When we gaze up at the night sky, we're confronted with a humbling sight. Countless stars twinkle against the dark canvas of space, but what we see is just a tiny fraction of the universe's true expanse. The universe is mind-bogglingly vast. To put it in perspective, imagine shrinking the Earth to the size of a grain of sand. At that scale, our entire solar system would be about the size of a football field. But the Milky Way galaxy? It would span North America. And that's just one galaxy among billions. The universe is not just big, it's cosmically big. It's a realm where distances are measured not in miles or kilometers, but in light years. The question, how big is the universe? Seems simple. But it's one of the most profound and challenging questions in science. We've come a long way in our understanding, yet in many ways we've only scratched the surface. As we delve into the cosmic scales and latest discoveries, prepare to have your mind expanded. We're about to embark on a journey from our tiny blue planet to the very edges of the observable universe. So buckle up, it's time to explore the true scale of our universe. The observable universe is everything we can potentially see from Earth. It's like a cosmic bubble centered on us. This bubble has a radius of about 46 billion light-years. But here's the kicker. This is just the part we can see. The actual universe could be much, much larger, maybe even infinite. Why can we only see so far? It's because of the speed of light. Light travels fast, about 186,000 miles per second. But the universe is so vast that even at this breakneck speed, light from the farthest reaches has only just reached us. The light from these distant regions has been traveling for almost 13.8 billion years. So when we look at the edge of the observable universe, we're seeing it as it was shortly after the Big Bang. While light has been traveling towards us, space itself has been stretching. This expansion means that the most distant objects we can see are now much farther away than when their light first began its journey to us. The observable universe contains an estimated 2 trillion galaxies. Each of these galaxies contains billions of stars, yet this might be just a tiny fraction of what's out there. Our entire observable universe, as vast as it is, could be just a small pocket in an even greater cosmic ocean. How do we measure such vast distances? Scientists use what's called the cosmic distance ladder. It's a series of techniques, each building on the last. We start with what we know and use it to measure what we don't. It's like climbing a ladder, with each rung taking us further into space. The first rung might be measuring distances within our solar system. The next might be to nearby stars, then to distant stars in our galaxy, and finally to other galaxies and beyond. One of the earliest methods used was parallax. It's based on the apparent shift in position of nearby stars as Earth orbits the Sun. By measuring this tiny shift, astronomers can calculate the distance to stars up to about 1,600 light-years away. For more distant objects, we use what are called standard candles. These are astronomical objects with known luminosity. By comparing how bright they appear from Earth with how bright we know they actually are, we can figure out their distance. One important type of standard candle is a kind of exploding star called a type Ia supernova, but even these methods have their limits. For the most distant objects, we rely on the redshift of light. When dealing with the vast distances of space, our everyday units of measurement fall short. Miles and kilometers just don't cut it. Instead, astronomers use light years and parsecs. A light year is the distance light travels in 1 year. It's about 5.88 trillion miles or 9.46 trillion kilometers. To put that in perspective, light from the Sun takes about 8 minutes to reach Earth. But light from the next nearest star system, Alpha Centauri, takes over 4 years to get here. The parsec is another unit commonly used in astronomy. 1 parsec is about 3.26 light years. The name comes from parallax second, referring to the parallax method we discussed earlier. Specifically, 1 parsec is the distance at which an object would have a parallax of 1 arcsecond. Our Milky Way galaxy is about 100,000 light-years or 30,000 parsecs across. The nearest large galaxy to us, Andromeda, is about 2.5 million light-years away. The most distant galaxies we can see are billions of light-years away. When we look at these far-off objects, we're seeing them as they were billions of years ago. It's like looking back in time. Section 5. The Expanding Universe, a Cosmic Revelation. One of the most groundbreaking discoveries in cosmology was that the universe is expanding. This idea was first proposed by Georges Lemaitre in the 1920s and confirmed by Edwin Hubble in 1929. Hubble observed that distant galaxies were moving away from us. Not only that, but the farther away a galaxy was, the faster it was receding. This relationship, known as Hubble's law, is a cornerstone of modern cosmology. The expansion of the universe is often compared to a balloon being inflated. Imagine drawing dots on a balloon to represent galaxies. As you blow up the balloon, all the dots move away from each other. From the perspective of any single dot, all the others appear to be moving away. This is similar to what we observe in the universe. It's not that we're at the center of the expansion. Every point in the universe sees the same thing. This expansion has profound implications. For one, it suggests that if we run the clock backwards, everything in the universe would converge to a single point. This leads to the idea of the Big Bang, the moment when the universe began. The expansion also affects how we see distant objects. As space stretches, it stretches the light traveling through it. This is what causes the redshift we mentioned earlier. But the expansion of the universe isn't just continuing, it's accelerating. Section 6. Galaxies and superclusters, cosmic building blocks. Galaxies are the fundamental building blocks of the large-scale structure of the universe. Our own galaxy, the Milky Way, contains an estimated 100 to 400 billion stars. But it's just one among billions of galaxies in the observable universe. Galaxies come in various shapes and sizes. There are spiral galaxies like our own, elliptical galaxies, and irregular galaxies. Some are dwarfs with just a few million stars. Others are giants with trillions of stars. But galaxies aren't randomly distributed through space. They're organized into larger structures. The first level of organization is galaxy groups. Our Milky Way, for example, is part of the local group, which includes the Andromeda Galaxy and about 80 smaller galaxies. Galaxy groups then form even larger structures called galaxy clusters. These can contain hundreds or even thousands of galaxies, all bound together by gravity. The Virgo cluster, the nearest large cluster to us, contains about 1,500 galaxies. The organization doesn't stop there. Galaxy clusters themselves are grouped into even larger structures called superclusters. These are among the largest known structures in the universe. Section 7. Dark matter and dark energy, the invisible majority. When we look out at the universe, we see stars, galaxies, and clouds of gas and dust. But this visible matter is just the tip of the cosmic iceberg. Scientists have discovered that about 95% of the universe is made up of substances we can't see directly. These mysterious components are known as dark matter and dark energy. They're called dark not because they're actually dark in color, but because they don't interact with light in ways we can detect. Dark matter makes up about 27% of the universe. We can't see it, but we can detect its gravitational effects. It acts like an invisible glue, holding galaxies and galaxy clusters together. Without dark matter, galaxies would fly apart because they're spinning too fast for their visible matter to hold them together. We see evidence for dark matter in the way galaxies rotate, in the motions of galaxies within clusters, and in the bending of light by massive objects, known as gravitational lensing. Despite this evidence, we still don't know what dark matter is made of. It's one of the biggest mysteries in modern physics. Even more mysterious is dark energy, which makes up about 68% of the universe. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. It seems to be a property of space itself. As the universe expands, it creates more space, and this new space contains more dark energy. This causes the expansion to speed up. Section 8. The cosmic microwave background. Echoes of the Big Bang. One of the most important discoveries in cosmology was the detection of the cosmic microwave background, or CMB radiation. This faint glow coming from all directions in space is the afterglow of the Big Bang. It's the oldest light in the universe, emitted about 380,000 years after the Big Bang. The discovery of the CMB in 1964 by Arno Penzias and Robert Wilson provided strong evidence for the Big Bang theory. It earned them the Nobel Prize in Physics. The CMB is incredibly uniform. No matter where we look in the sky, its temperature is almost exactly the same, about 2.7 degrees above absolute zero. But almost is the key word here. There are tiny fluctuations in the temperature, at the level of about 1 part in 100,000. These tiny differences are incredibly important. They're the seeds from which all structure in the universe grew. Over billions of years, gravity amplified these tiny fluctuations, leading to the formation of galaxies and galaxy clusters. Studying the CMB has revolutionized our understanding of the universe. Section 9. Methods of measurement. Peering into the cosmos. Measuring the vast distances and scales of the universe is no easy task. Scientists have developed a variety of ingenious methods to probe the cosmos. One fundamental technique is spectroscopy.